Hello, this is Reza Godaz. I want to talk about our paper, Vector Transport Free Riemannian LBFGS for Optimization of Symmetric Positive Definite Matrix Manifold with my friend Benyamin Ghojogh. First of all, in Riemannian optimization problems, we are trying to minimize a function such that each point of this function is selected from a Riemannian manifold. Riemannian manifolds are smooth manifolds equipped with Riemannian metric. Our first mapping is named inverse second root. As you can see here, our mapping is applied on a vector at the tangent vector of a point. After applying our mapping, the Riemannian metric that you can see at the top of the page is changed to Euclidean inner product, as you can see at the bottom of the page in the red rectangle. As you can see here, a complex formula with a more time complexity to compute is changed to a simple formula with less time complexity. And also vector transport that has a complex formula is changed to an identity operator that doesn't need any time to compute. Our second mapping is Cholesky decomposition. This mapping is used on vectors in the tangent vector of a point, such as our previous mapping. Using this mapping, Riemannian metric, and as you can see here on the red rectangle at the top of the page, it changed to Euclidean inner product that is very simpler than Riemannian metric about time complexity and also complexity of the formula. And also about vector transport, it is a complex formula. After our mapping is changed to an identity operator that doesn't need any time to compute.
Okay, now we talk about the RLBFGS algorithm, and as you can see here, the Riemannian LBFGS algorithm is just an extension of LBFGS algorithm to Riemannian world. For the LBFGS algorithm, you can refer to the Nocedal and Rice book on optimization. It's just quasi-Newton's method for optimization. And as you can see, we have we have a body of algorithm in which we find a direction, and with a line search we find the step size. The getting direction function is a recursive function which has a memory. And as you can see, in the get direction function, we have transports and vector transports, where vector transport just maps a point from one tangent space to another tangent space on that manifold. Here you don't see the vector transports and adjoint vector transports because in this page, because by our mappings the algorithm becomes vector transport free. Here we are showing you the lines of the algorithm where our mapping is not yet applied. And as you can see, when calling the recursion inside the recursive function, you can see we have vector transport for going from one point to another point. And this is very time consuming to compute. Also, we have adjoint vector transport, which is kind of like the inverse vector transport, but not exactly that. It brings the next point to the previous point. Also, we have in equation 6 and 7 here, which we had in the main body of algorithm, as you can see in the left-hand side. We have vector transports which are time-consuming to compute. Also, in equation 4, which is called inside the recursive function, we have metrics which are time-consuming before applying our mapping. And when we applied our mappings, many operators have become simpler in the algorithm. And as you can see, the time complexity has been improved. The time complexity is theta m n 2 after applying our mapping, whilst it was m n 3 before. Why? Because metric before applying our mapping requires theta n cubed, while when we have trace of just inside trace we vectorize matrices, therefore it becomes theta n squared after applying our mapping. Vector transport also has become identity, so it becomes theta 1 after our mapping. And we have done some experiments on two experiments actually. For the first extensive experiment we did on Gaussian mixture models, where we have just a mixture of Gaussians, and we want to find the mixing probabilities as well as means and covariances of the Gaussian distributions, where the covariance matrices belong to the symmetric positive definite matrix manifold. Please note that we are in this paper we are focusing on symmetric positive definite manifolds. Therefore, our applications and experiments must be in the area of symmetric positive definite. And as you can see, we have compared with expectation maximization algorithm for fitting a mixture model, as well as a conjugate gradient and RLBFGS without our mappings. Here in the caption, you can see in the legend, you can see VTF means vector transport 3, which are our mappings, and ISR and Cholesky are two mappings that we have proposed. And as you can see, we have outperformed all the baselines in terms of number of iterations here. Also, we have found better local minimums. And as you can see, the other experiment that we had was on geometric metric learning, and where we want to find the metric in the metric inside the metric W. And as you can see, the W matrix inside the metric must be positive semi-definite to satisfy triangle inequality and convexity of the metric. And as you can see, we have compared our algorithm to the not applying our mapping, and we have experimented on three datasets: Iris, USPS, Digits dataset, and MDIS dataset. And as you can see, in different occasions, we have outperformed the baseline in terms of number of iterations, convergence time, time of every iteration, and the found cost function. Thank you very much.